Today is the lecture for Monday, March 30th. We will be continuing our discussion of quantum chromodynamics, and we'll first start by talking about the gauge group SU3. SU3 stands for, the 3 is for 3 by 3 matrices, so we have a 3 by 3 matrix. And you can think of these matrices as multiplying a 3-component column vector. So you might think of these being red, green, blue, or the ordering doesn't matter, whatever convention you want. And so these are the matrices, the elements of the what we call the Lie group. The words, remember, special refers to the fact that the matrix, let's call it U, the determinant of U is equal to 1. The U here stands for unitary, and that means that the U Hermitian conjugate is equal to the inverse of U. So remember, the Hermitian conjugate is taking the transpose of the matrix and complex conjugating all the elements. All right, now as an aside, let's remember we've talked about a simpler Lie group called SU2, and so SU2 stands for the special unitary 2 by 2 matrices. So in this case, we have 2 by 2 matrices, and we were discussing this in the context of doing rotations of spins for a spin 1/2 particle. We have an upspin and a downspin. Okay, so these Lie group elements for SU2, we said that we could write down these elements as at least the ones that are continuously connected to the identity matrix. These could be written down as the exponential of I times theta 1 times sigma 1 plus theta 2 times sigma 2 plus theta 3 times sigma 3. Okay, so these guys here are elements of what we call the Lie algebra. So hopefully you are remembering back to the first few weeks of the class when we did a lot of work on group theory and Lie groups and Lie algebras. All right, so you may recall when we talked about these elements of Lie algebras, these things had to be Hermitian. So the things I'm putting in here has to be Hermitian. And the fact that, so remember, this is again the special unitary 2 by 2 matrices, and the fact that it's special means that the determinant is equal to 1. Okay, and to make the determinant equal to 1, it turns out that the matrices here have to be Hermitian and also trace 0 or traceless. So remember, the trace is the sum of the elements along the diagonal. And there turns out to be only 3 linearly independent matrices you can write down of this form: sigma 1, sigma 2, and sigma 3. And these are the well-known Pauli matrices. Okay, you'll notice that they're Hermitian and they are traceless. Summing the diagonal entries give you 0. So now let's go back to SU3 again. We can do the same thing. We can take these elements of the Lie group that are close to the identity, and we can expand these as an exponential of I times some linear combination of theta 1, lambda 1, theta 2, lambda 2, theta 3, lambda 3. There'll be 8 of them in this case. Theta 4, lambda 4, theta 5, lambda 5, theta 6, lambda 6, theta 7, lambda 7, theta 8, lambda 8. All right, and again, they will the Hermitian traceless 3x3 matrices. So let's try to count how many such matrices there are. For the case of 2x2 matrices, how does this work? Well, if I have a 2x2 matrix and it's Hermitian and traceless, then the complex conjugate of what I have here must equal what I have there. So this is not another degree of freedom. So I have the real part and the imaginary part of this element here. Okay, so that's 2 real degrees of freedom. And then this must be real because it must be Hermitian. This must be real because it must be Hermitian. But the sum of these two must equal 0. So only one of these two is linearly independent. So it's so then I get 2 plus 1 is equal to 3 real parameters that parameterize the Hermitian traceless matrices. The same counting goes here, right? It turns out, in this case, to be Hermitian, you end up with 9 real parameters. So basically the real imaginary parts of this, the real imaginary parts of that, the real imaginary parts of that, and the real part of this, real part of that, real part of that. That turns out to be 1, 2, 3, 4, 5, 6, 7, 8, 9. But then to make it traceless, one of these combinations it must be 0, so there's only 8. So there'll be 8 linearly independent elements of our Lie group, our Lie algebra, sorry. Okay, and so the standard way of writing down these matrices, these Hermitian traceless matrices, are what are called the Gell-Mann matrices, and they look sort of like the 3x3 version of the Pauli matrices. So these guys, I said it but I didn't write it down, these are the Pauli matrices. There are 3x3 versions of the Pauli matrices for various combinations of 2x2 subspaces of the 3x3 space, at least for most of them, but then the diagonal ones are a little bit different. So lambda 1 has the form 0, 1, 0, 1, 0, 0, 0, 0, 0. So that should remind you of the Pauli matrix for this little upper left-hand corner. And then lambda 2 is 0 minus I, 0, I, 0, 0, 0, 0, 0. And this again looks a lot like sigma 2 here. Now then lambda 3 is going to be 1, 0, 0, minus 1, like that, and zeros elsewhere. Looks a lot like the sigma 3 matrix. Now, for the others, then we have a different combination. Now, this time we take the outer elements like this. Okay. So you can think of this as coupling 1 and 3, rows 1 and 3, or columns 1 and 3. Lambda 5 will then have the form 0, 0, minus I, 0, 0, 0, I, 0, 0, like that. And then lambda 6 will have the form 0, 0, 0, 0, 0, 1, 0, 1, 0. And lambda 7 will be 0, 0, 0, 0, 0, minus I, 0, I, 0. And then lambda 8 will have a slightly different form. It will be 1 over square root of 3. To get things normalized in the proper way, 1, 1, minus 2. So it has to be traceless, that's why it has that 1, 1, minus 2 form to it. Okay, so these guys are the Gell-Mann matrices. Okay, so now the quarks then are, you can think of the quarks as belonging to or corresponding with the red, green, and blue that you get with this 3-component column vector, but the gluons will correspond with these things we're putting in the exponent here, so the Lie algebra. It's the Lie algebra for are SU3. Okay, and so there are 8 linearly independent elements of our Lie algebra, and so there will be 8 gluons. And you can think of then these matrices, these elements of the Lie algebra as making conversions. For example, if I think of the top 2 as being red and green, then I can think of this matrix as somehow interchanging red and green. Okay, and if I think of the outer ones as being red and blue, this is interchanging red with blue. And so that's one way to think about what's going on with the colors for the gluons. So I know that was sort of a long build-up to explain what's going on here. So we can think of the gluons as carrying color, but you can think of it as some combination of one of the colors and then taking away one of the colors, just like I said here. It's going to exchange red and green, so you take away, let's say, green, and then you add a red. Okay, so you can think then of a gluon as having a color and an anticolor. So I can make a little color chart here. So I have red, green, blue. Okay, and then you can have in between things. So combine red light with green light. Turns out it gives you something that's yellowish, but you can think of this as being anti-blue. All right. By the way, adding colors of light together is different from adding together pigments. Now, I can also have a combination of red with blue. It gives you something that looks violet, although it's not the same thing as the pure light frequency violet. It has the eye perceives it as looking like violet. It's a mixture color, and that would be the same thing as anti-green. So the yellow was anti-blue, the violet is anti-green, and then if you have a combination of blue with green, then you get something that looks what's called cyan, and that would be the same thing as anti-red. So if I have red with green with blue together, I get something that's white or colorless. But if I have blue with anti-blue, then I get colorless. If I have red with anti-red, I get colorless. I have green with anti-green, I also get colorless. Okay, so that's one way to think about all of this. The gluons are binding together the quarks, and they have some combination of color with anticolor like this. Now the quarks then have red, green, blue, but then the antiquarks will have anti-red, anti-green, and anti-blue. Okay, so this is what we've just discussed. So what is the total number of gluons? So we just went through this according to the group SU3. These 3x3 color combinations form a singlet and an octet. So I'm not going to, let me just tell you then, this term octet is referring to the set of 8 of these elements. Okay, the singlet refers to the fact that there's another traceless Hermitian matrix that would be proportional to the identity matrix. Okay, so something proportional. This is the identity matrix, by the way, but that would not have any color to it. The gluons do have color, so those are these 8 elements, and they can be written down in this form, and they're supposed to remind you of what I've written here: red-green mixture. Okay, so red with anti-green, red with anti-blue, green with anti-blue, green with anti-red, blue with anti-red, blue with anti-green, and then we have these interesting combinations where we have some diagonal terms where we have red with anti-red minus green with anti-green, and then we have here red with anti-red plus green with anti-green minus 2 times the blue with anti-blue. Okay. All right. So now, and then you can also make a color singlet object, which is not one of the gluons, but this combination red with anti-red plus green with anti-green plus blue with anti-blue is what you call a color singlet. All right, so now we can picture what's going on with the colors when the the gluons are acting upon quarks. So you can imagine, for example, the emission of a gluon by a quark. You have a quark going to a quark plus a gluon. Okay, so you have red quark coming in. The red continues on, but you have green then being produced with anti-green, and so the gluon that you produce will be red with anti-green. Right. Same kind of deal here. You may have the splitting of a gluon into a quark anti-quark pair. So in this case, you might have red with some anti-green, and then you will then have anti-green quark with a red quark. Okay, and then you can have a more complicated vertex where you have two gluons. One gluon splitting into two gluons. You can follow all the various color lines here. Okay, and so here's some picture with some stuffed toy things that if you like these things, I think you can order them at the particlezoo.net, showing the various colors for the quarks and the antiquarks and the gluons. Okay, so now let's talk a little bit more about the quarks. We've discussed them a bit already. So a quark, first of all, at the basic level, if I have three quarks together, that's enough to form a baryon. So that's why when we talk about the baryon number A, the quarks will have, the individual quarks will have baryon number 1/3. Okay, so for example, a proton will be at the bare level an up and a down quark. A neutron will be up, down, down. Okay, so each one of these quarks will have a baryon number of 1/3. Okay, now, so the up quark will then have baryon number 1/3. It will have, so this is referring to isospin. So remember, the up and the down quarks, they form an isospin doublet. So the isospin equal to 1/2. Just like a spin 1/2 particle, we have this isospin that rotates the up with the down. This is something we've already discussed in the context of the isospin of the proton and neutron. That's also isospin 1/2. Okay, so the up quark is considered to have z component isospin equal to +1/2, whereas the down quark has -1/2. And so they rotate into each other according to isospin. Now then you can also write down quantum numbers corresponding with strangeness, charm, bottom, and top. Okay. Now the strange quantum number is just counting the negative the number of this number of strange quarks. You might ask why would strangeness correspond with the negative of the number of strange quarks? Is because they didn't know which one was which, and they hadn't set the convention. So that's just the way it ended up. Okay, and so for the strange quark, so I didn't tell you much about the end of this table here. The up quark has a charge of +2/3, and the down quark has a charge of -1/3. And we've already discussed this before. The mass is about 2.3 or so MeV for the up quark and about 5 MeV for the down quark. Now for the strange quark, it's like the heavier version of the down quark, so it has a charge of -1/3. The charm quark is like a heavier version of the up quark, so you can then again assign this quantum number called charmness. So charm quark has 1 unit of charmness to it. Okay, and so because it's a heavier version of the up quark, it has a charge +2/3 and it has a mass. Okay, so coming back here, the mass of the strange quark is about 100 MeV, and the mass of the charm quark is about 1,200 MeV. And for the bottom quark, it's a lot like the heavier version of the down or the strange quarks. You can assign then a bottomness, so it has a bottomness of -1, and it has a charge -1/3, and it's about 4,200 or so MeV. And the top quark is the heaviest of them all, and it has some quantum number which we call topness, and it has a charge of +2/3. It's like a heavier version of the up and the charm quark, and it has a very large mass, about 173 gigaelectron volts. Okay, we will later talk about various symmetries, approximate symmetries, where we think of the up and the down quark as being degenerate, so that's isospin symmetry, okay? But we also can talk about the case when the up, down, and strange quark have approximately the same mass as well, or perhaps even consider that they all are massless. Now, there are, of course, the antiquarks for all of these. They have the same masses. They will have the opposite charges, and, the opposite strangeness, charmness, bottomness, and topness to it. Okay. Now, so I mentioned that we have this isospin symmetry, so I can talk about a isospin lowering operator that takes you from the up quark and it brings you down to the down quark, and then this raising operator will take you from the down quark and bring you up to the up quark. So now, a meson is a combination of a quark with an antiquark, okay? Whereas a baryon is at the base level 3 quarks. And for the glue ball, that's some combination of gluons. Exactly how many gluons you have is to be determined. But the minimum number that you can have would be 2, like this. Okay. So now, for meson, we have then a quark and an antiquark line like this. So you can imagine having something like the pi plus meson, which is at its simplest level an up and a down anti-down quark. So you can have 3 various colors combinations. So all of the hadrons, all of the particles that we observe in nature have to be colorless. So they have to be combined into some combination that has no color to it. So it needs to be a combination of red with anti-red plus blue with anti-blue and green with anti-green, like this. Okay, so that can be achieved by just having these colors aligned in that fashion, red with anti-red, like this. But it can switch to green with anti-green just by exchanging a gluon that carries red anti-green color to it, so that the red leaves, the green is produced here because it has to be has to balance off the anti-green coming with the gluon, and then the anti-green then will flow over here, and the redness will annihilate the anti-red over here, so you get a green with anti-green, and so on. So you can go from red anti-red to green anti-green, blue to anti-blue, and maybe back to green anti-green. So there are 2 general types of strongly interacting particles. So hadrons are basically any strongly interacting particles, things that interact through quantum chromodynamics. Okay, so baryons were these things. So baryon, the word baryon, the root has to do with the word heavy, whereas meson is sort of in between. So baryon, you have 3 quarks, whereas meson is quark-antiquark. Okay. And because the quarks are fermions, spin 1/2 particles, these baryons will have half-integer spins to them, but the mesons will have an integer number of spins. All right, so we can consider then all possible interactions. For example, proton with antiproton can produce 2 photons. So that's how you can produce a zoo of particles by banging together particles, for example, proton, antiproton, see what you get out. So the particles and antiparticles have opposite charges, opposite baryon numbers, etc. They have everything opposite except for the fact that the masses are the same. Okay, there's no negative mass particles. They must have opposite intrinsic parities to them. Okay, so that's, for example, the quark has, let's say, 1 parity, then the antiquark must have the opposite parity to it. And they must have also the opposite isospin. Okay, so let's just write down a very simple rule to make the connection between the charge and the baryon number. Okay, so let's just do this at the quark level. So let's just do this for the up and down quarks, right? So the charges of the up and down quarks are plus 2/3 and minus 1/3. Up quark is plus 2/3, the down quark is minus 1/3. So the isospin T0, the Z component, the zero component, T0 of this guy will be plus 1/2 for up and then minus 1/2 for down. If I write down the baryon number over 2, I said each one of these is 1/3, so baryon number over 2 would be 1/6. And so if I add T0 plus A over 2, 1/2 plus 1/6 gives me plus 2/3, minus 1/2 plus 1/6 gives me minus 1/3, which is exactly what we get for the charges. Okay, so that's how we get the charges as this combination. And by the way, this little game that I played seems like just playing around with numbers, but this is actually how these charges seem to be coming about by this unification of the electromagnetic and the weak interactions. You actually get this combination, and this combination is what actually ends up being the electric charge. So it's deeper than just playing around with these numbers. Okay. So then you can also talk about what's happening with the antiquarks. So there's this charge conjugation operator that converts the quarks to the antiquarks. So let me maybe finish this lecture talking about the mesons. So this is a lot like putting together, if we're thinking about the isospin of the mesons. So the isospin of the mesons, we have combinations of quark with antiquark. Okay. But we can make this connection with spin 1/2, just spin 1/2 particles. So let's say I can have spin up, and I can have spin down. That's spin 1/2. But then we talked about adding these together, or having two such spin 1/2 particles. What types of spins can we have total? So we said we can have a combination of two up spins, and that will give me a spin 1 combination, where in this case the Jz value, so this will be J equals 1, or spin 1, and the Jz value will be plus 1. Okay, then I can lower the spin, the Jz value, and I can have this combination, up with down and plus down with up, and this will be Jz is equal to 0, and then I can lower it again, where both are pointing down. This is Jz equals to minus 1. All right. Then we've also said that we can have J equals to 0. Okay, so that's the spin 0 combination. And this is going to be the combination that's orthogonal to this guy here. And that orthogonal combination was 1 over the square root of 2, up with down, minus down with up. Okay. And this was a statement that if I have a spin 1/2 particle with this another spin 1/2 particle, I get a spin 1 and I get a spin 0. Right? That's all I get, and that's exactly what we've written down here. We can do the same thing with isospin, and if I combine a quark and an antiquark together, and so the quark has isospin 1/2, and the antiquark also has isospin 1/2. Okay. So the combinations I can get will be isospin 1. So then I would get these combinations where I have sorry, you can't see that. I can have the pi minus, which is anti-up with down. And then I can have a pi 0, which I can get from raising this guy and getting up with anti-up minus down with anti-down, normalized with the factor 1 over square root of 2. And then I can get a pi plus, that would be up with an anti-down. Okay, that's supposed to be reminiscent of what I have here with my spins. But then there's one last combination that's that I didn't cover, and that's going to be the remaining combination like this here, which would be up with anti-up plus down with anti-down. Okay. All right. So next time we will continue this further and talk about the extension to 3 quarks, and that will be the work of Gell-Mann, where you include the up, down, and strange quark.